December 7, 1941, marks a day that forever changes the Pacific. Pearl Harbor burns, battleships sink, and aircraft carriers disappear beneath waves, but another crisis quietly unfolds, far from the headlines. Across the islands of the Pacific, American forces face a problem that artillery and courage alone cannot solve: shelter. Soldiers sleep in canvas tents that collapse under relentless monsoon rains within weeks. Ammunition depots flood, uniforms mildew, and pneumonia spreads faster than enemy bullets. The War Department's morning briefings grow grim as reports arrive, tents disintegrate, barracks cannot be built fast enough, and thousands of troops are exposed to disease and exhaustion. Traditional wooden barracks demand skilled carpenters, weeks of labor, and lumber that simply does not exist on remote coral atolls. The Navy calculates that constructing conventional housing for the thousands of men needed for Pacific campaigns would take 18 months they do not have. Brigadier General Eugene Raybould stares at maps and construction timelines in Washington. The task seems impossible: design a shelter that can be manufactured in Pennsylvania, shipped thousands of miles through submarine-infested waters, assembled by exhausted Marines with no construction experience, and survive the worst conditions the Pacific can throw at it: typhoons, monsoons, scorching heat, and the ever-present threat of Japanese attacks. The stakes are high. A standard army tent costs $12 but will last only a month in the jungle. A wooden barracks costs $8,000 and takes 6 weeks to build. Neither option works for the strategy of island hopping across thousands of miles of ocean. Soldiers write home with tales of waking to mud-filled boots, uniforms covered in fungus, and shelters torn apart by sudden storms. Respiratory infections and exposure hospitalize more men than bullets or bombs in some sectors. This is not just inconvenience. It threatens the very ability of the United States to fight. In search of a solution, Raybould's team looks abroad. The British, hardened by years of combat in North Africa, offer an example. Since World War I, they've used Neeson huts, semicircular steel structures designed by Canadian engineer Peter Neeson. These huts house 30 men, require minimal skill to erect, and withstand desert sandstorms. But the Neeson design, while brilliant for the deserts of Libya, is flawed for the Pacific. The steel panels are heavy, ventilation is inadequate for tropical humidity, and every hut demands a foundation, bringing the project back to the problem of scarce materials and skilled labor. The British lessons are clear: traditional approaches will fail. By February 1942, somewhere in Rhode Island, American engineers begin turning impossibility into reality. The Navy receives technical drawings of the Neeson hut, and Commander John Philip Drosfeld quickly identifies both genius and limitations. The arch shape deflects wind naturally, but heavy steel, wooden frames, and poor ventilation threaten survival in the tropics. The team studies Buckminster Fuller's writings, whose radical ideas about prefabrication and mass production, once dismissed as impractical, now appear prophetic. Fuller's philosophy, treat buildings as manufactured products, not traditional construction, fits the moment. Shelter must be designed for speed, efficiency, and maximum resilience. At Quonset Point, Rhode Island, the Navy assembles an unprecedented team of engineers, architects, and officers familiar with Pacific conditions. Otto Brandenberger, an engineer with experience in self-supporting steel barns, proposes eliminating the wooden skeleton entirely, letting the steel arch bear all loads. This violates every conventional rule of architecture, but it leverages the physics of arches, turning structural necessity into opportunity. British reports inform every design choice, highlighting fungus, humidity, insects, and corrosion as enemies to overcome. Every detail, from fasteners to ventilation, is reconsidered with tropical warfare in mind. By April 1942, the vision crystallizes. Take the genius of the Neeson arch, remove what makes it heavy or vulnerable, and integrate Fuller's mass production principles. Steel becomes the medium, prefabricated and lightweight, capable of being shipped flat, assembled quickly, and surviving the extremes of war. The problem is daunting, the clock is ticking, and the lives of tens of thousands of servicemen depend on the ingenuity that follows. With the Quonset vision defined, the real work begins. Prototypes must be created fast, and the team at Quonset Point faces a grueling 60-day deadline. Weeks of calculations, sketches, and trial-and-error experiments converge in a warehouse that transforms into a laboratory of steel, sweat, and ingenuity. Every detail matters. The panels must be light enough for 4 men to carry, yet strong enough to survive 100 miles per hour winds and tropical downpours. The arch must be precise, too flat, and the wind could rip the structure apart, too steep, and interior space is wasted, complicating assembly. Brandenburger divides his crew into specialized teams. One focuses on aerodynamics and structural loads, another on how components will nest for shipping, and a third on joints and fasteners, the Achilles heel of every previous design. Traditional architectural methods are abandoned. Instead of final drawings months before construction, the engineers adopt an iterative approach: sketch a component in the morning, fabricate by afternoon, test overnight, and refine by dawn. By modern standards, this is rapid prototyping. In 1942, it is revolutionary. Failed experiments litter the warehouse: bent panels, broken joints, and discarded hardware, but each failure brings insight. The dimensions settle on practicality. 16 feet wide, 20 feet long per section, 48 feet total when assembled. This size maximizes shipping efficiency without overburdening troops in the field. 36 men can sleep in bunks, or the space can be converted into medical stations, offices, or supply storage. The arch is calculated with precision, forming a self-bracing curve that allows the panels to remain thin yet resilient. Corrugations run lengthwise, acting like tiny I-beams, adding rigidity and preventing bending forces from compromising the structure. Every bolt, every seam, every panel placement is optimized for the harshest imaginable conditions. The first full prototype goes up in May 1942. 6 sailors, with only 4 hours of instruction, assemble the hut with hand tools. 14 hours later, a crude but functioning structure stands. The floor, initially included, slows assembly and rots in humidity. The engineers eliminate it entirely, allowing the hut to sit directly on sand, coral, or dirt. This decision reduces weight, simplifies logistics, and accelerates assembly to 8 hours, still longer than the ideal, but already a breakthrough. Testing intensifies. The hut must withstand wind, rain, humidity, and tropical pests. In Rhode Island, nor'easters simulate severe wind loads. Strain gauges and pressure sensors record flex and deflection. The structure endures, returning to its original shape after storms. A test unit is shipped to the Panama Canal zone to simulate tropical conditions. Humidity and heat reveal new challenges. Condensation forms on cooler steel surfaces, creating raining ceilings inside the hut. The solution is ventilation. Louvers along the ridge and ends allow hot air to escape while preserving structural integrity. A minor increase in cost, but the difference between a steel sauna and habitable shelter. Anchoring is the next problem. How to secure a 9,000-pound building on sand, coral, or uneven soil without pouring concrete. The team borrows from tent technology. Steel stakes and tension cables stabilize the hut, while wooden sleepers or pierced steel planking allow placement on harder surfaces. The design is forgiving, flexing slightly with the ground to survive typhoons rather than cracking under stress. Field tests confirm the concept. By June 1942, the prototype is complete: 96 steel panels, each under 50 pounds, bolted together into a 720-square-foot structure. The design is simple, elegant, and deadly practical. The Navy approves production, and the factories respond. Strand Steel in Pennsylvania, George A. Fuller Construction in Chicago, and Great Lakes Steel retool, shifting from civilian industry to military emergency housing. Corrugated panels are mass-produced, galvanized for corrosion resistance, and packaged efficiently. Each hut nests for shipping, including end walls, bolts, and illustrated assembly instructions. One standard railcar carries enough panels for a complete hut, maximizing limited transport space. Meanwhile, engineers continue refining the design. Feedback from field deployments leads to stronger fasteners, improved ventilation, and adjustments for tropical insects and corrosion. The Quonset hut is evolving even as production begins, a living testament to iterative engineering under pressure. Every lesson learned in the laboratory and from tropical experiments feeds back into the assembly line, ensuring that mass-produced units are not just fast, but durable. The Quonset prototype embodies the philosophy that drives wartime engineering: simplicity, speed, adaptability. It's not glamorous or aesthetically pleasing, but it solves the most pressing problem of the Pacific Theater: shelter, for tens of thousands of men, built fast enough to keep the fight going. By mid-1942, the Quonset hut had moved beyond prototype. The Navy's approval triggered an unprecedented mobilization of American industrial capacity. Factories that had spent the previous decade producing grain silos, automobile parts, and water tanks were suddenly retooled to churn out prefabricated steel huts. The Strand Steel Corporation in Pennsylvania dedicated its entire facility to Quonset production. George A. Fuller Construction converted a former auto plant in Chicago. Great Lakes Steel focused rolling mills exclusively on corrugated panels. Within weeks, assembly lines were producing hundreds of huts per week, a rate that would only accelerate as the war progressed. Mass production demanded precision. Steel coils, 4 feet wide and weighing thousands of pounds, were unrolled, corrugated at exactly 2.67 inches per ridge, and hardened through work processes. Panels were galvanized in molten zinc at 850 degrees Fahrenheit, creating a metallurgical bond that sacrificed itself to corrosion before the steel beneath could rust. In the Pacific salt-laden air, this difference meant the survival of thousands of servicemen. Each complete hut included 96 panels, end walls with pre-cut doors and windows, and all bolts and fasteners, packaged efficiently to fit on a single flatbed railcar. Every step, from factory to port, was choreographed to maximize speed and minimize loss. The shipping operation was a logistical ballet. Trains carrying huts departed daily from Philadelphia, Chicago, and other industrial hubs, arriving at West Coast ports where Liberty ships waited. Longshoremen loaded huts into ship holds using cranes designed for tanks and artillery. A single Liberty ship could carry 200 huts, enough to shelter 7,200 men. The War Shipping Administration monitored every shipment, aware that a missing hut could mean exposed troops in a typhoon-prone region. The true test began on the islands themselves. Guadalcanal, August 1942. The first combat-deployed Quonset huts arrived under blazing heat and near-constant Japanese air raids. Marine engineers, working amid artillery scars and scorched coconut groves, began bolting panels together. Within 12 hours, Henderson Field had 10 new structures ready for occupancy. Mechanics, medics, and supply personnel moved in, protected not by walls of wood or canvas, but by the precision-engineered steel arches. The first real trial came days later during a bombing run. A 500-pound bomb detonated 40 yards from a hut housing aviation mechanics. Trees splintered, tents shredded, yet the Quonset remained intact. The blast rattled steel panels and scattered debris, but no structure collapsed. Marines emerged shaken but alive. In the crucible of war, the Quonset's design proved its worth, a lightweight, prefabricated shell capable of surviving not only the elements but enemy attacks. The jungle environment tested the huts in ways Rhode Island never could. Salt, humidity, and fungus threatened corrosion and structural integrity. Early units suffered red rust on fasteners, and mold spread along damp walls. Ventilation proved insufficient, forcing field crews to prop doors open and cut additional vents. These modifications, though technically violations of specifications, made huts habitable and revealed critical insights. Feedback from the field was meticulously documented and sent back to Quonset Point, where engineers incorporated these lessons into subsequent production runs, improved ventilation, fully galvanized fasteners, and subtle design tweaks to resist tropical rot and corrosion. Meanwhile, production continued to scale. By December 1943, the factories were collectively producing 8,000 huts per month. The logistics network was astonishing. Huts ordered in Pennsylvania reached New Guinea within 40 days, including rail, port handling, and ocean transport. Every hut delivered shelter for 36 men at a fraction of the cost and time of conventional barracks. A wooden barracks would cost $12,000 in materials and take 400 man-hours of skilled labor to construct over 6 weeks. The Quonset, by contrast, cost $1,394 in materials and 60 man-hours of assembly. 1/10 the cost, 1/12 the time. The speed and adaptability of Quonset huts transformed military operations. Entire bases could be established in days, not months, allowing American forces to maintain momentum during the island-hopping campaigns. Engineers adapted huts to serve as offices, medical stations, ammunition depots, and supply warehouses. The same hut that sheltered Marines could be pressed into service as a field hospital or maintenance shop, demonstrating flexibility that conventional construction could never match. The combination of industrial might, clever engineering, and field-driven iteration created a cycle of continuous improvement. Feedback from tropical deployments informed design change. Bases across the region were leveled. Wooden barracks splintered instantly, and concrete block structures toppled as wind undermined their foundations. Of 43 Quonset huts on one affected base, 39 survived intact. 4 suffered reparable damage, bent panels, torn seams, but none collapsed. Engineers discovered the key factor: proper anchoring. Huts with well-placed stakes and tension cables rode out the storm, while those with insufficient anchoring were tossed aside like tumbleweeds. The lesson was clear: structural design was only part of the equation, deployment techniques were equally critical. Tropical deployment also revealed the challenge of condensation and interior humidity. Even fully galvanized panels trapped moisture in the steel shell, creating an uncomfortable rainfall inside the hut when hot days turned into cooler nights. Field modifications emerged almost instinctively. Marines cut additional vent holes, propped doors open, and experimented with airflow. These improvised solutions, though technically outside specifications, improved habitability. Engineers at Quonset Point documented these changes, incorporating larger ventilation louvers and fully galvanized fasteners into subsequent production runs. Meanwhile, Alaska presented the opposite extreme. The Aleutian Islands campaign subjected Quonset huts to Arctic conditions, temperatures plummeting below -40 degrees Fahrenheit and winds exceeding 100 miles per hour. Standard steel panels became brittle, and bolt holes cracked under stress. Engineers responded by specifying cold-rolled steel with altered metallurgy for Arctic deployments. Rubber gaskets were added at every joint to maintain flexibility, preventing panels from splitting under thermal contraction. Internal insulation batting and double-wall construction were introduced to conserve heat while managing condensation. Even ventilation required careful calibration to avoid freezing moisture inside while preventing suffocating air buildup. Field crews adapted quickly, learning to combine these engineered improvements with practical solutions. They improvised foundations on volcanic or sandy soil using oil drums filled with sand, while Arctic crews added insulation blankets and temporary floorboards. Each adaptation was documented and fed back into production, creating a continuous cycle of refinement. By mid-1944, Quonset huts had evolved from a prototype warehouse experiment into a highly adaptable, field-tested system capable of thriving in environments ranging from tropical jungles to Arctic winds. Combat conditions added yet another layer of stress testing. In Sicily and North Africa, Quonset huts functioned as ammunition depots and field hospitals. In one instance, a hut survived a direct hit from an 88mm artillery shell, which penetrated the steel skin and detonated inside. The arch-shaped structure distributed the blast force outward, leaving the frame twisted but standing. A rectangular building would have collapsed entirely, trapping anyone nearby. This reinforced the fundamental genius of the arch. Compression rings and load-sharing panels provided resilience even in catastrophic scenarios. The iterative process of feedback, design modification, and redeployment became standard practice. By the end of 1944, every major theater of operations had Quonset huts in use. Tropical variants featured enhanced ventilation and corrosion-resistant fasteners, Arctic models incorporated insulation and flexible joints, and combat modifications included reinforced end walls for munitions storage. No matter the environment, the basic principles remained constant: self-supporting steel arches, prefabricated components, minimal tools for assembly, and rapid deployment. By war's end, the Quonset hut was more than just a shelter, it was a symbol of adaptability, industrial ingenuity, and logistical mastery. The lessons learned in Rhode Island warehouses, Pacific beaches, and Arctic tundra formed a blueprint for modern prefabricated structures, disaster relief housing, and even future military deployments. Engineers had turned impossible requirements, speed, durability, cost efficiency, and versatility, into a tangible reality, setting a precedent for mass-produced, field-tested architecture that would echo far beyond World War II. With the war over in 1945, the United States found itself in possession of roughly 170,000 Quonset huts scattered across 6 continents. Initially designed as temporary military shelters, these structures faced an uncertain future. The original plan had assumed they would be scrapped or abandoned once conventional facilities could be built. But the reality of post-war America was far more complex. Cities faced housing shortages, returning veterans needed homes, and the construction industry struggled to ramp back up after years of wartime focus. Commanders and military base managers, confronted with the task of decommissioning thousands of huts, saw something unexpected: these were functional, durable buildings that required minimal maintenance. The War Assets Administration, tasked with liquidating surplus property, encountered a peculiar problem. Demand for Quonset huts exceeded supply. Veterans could purchase complete structures for $1,000 to $2,500, a fraction of the $8,000 cost for a conventional building, and municipalities and institutions quickly recognized their utility. Housing became the first major civilian application. Suburban developments, particularly around major cities, sprang up almost overnight. Roger Young Village in Los Angeles, for example, housed 750 families in converted military huts. Quonsets were adapted with wooden facades to soften their utilitarian appearance, while interiors were partitioned into bedrooms, living rooms, and kitchens. Some families buried huts partially underground for added insulation or connected multiple units to create larger compounds. These modifications made the structures livable while maintaining the original steel shell's integrity. The shortage of conventional housing also intersected with the GI Bill, which sent thousands of veterans to universities. Campuses faced overcrowding and immediate housing needs. Quonset huts provided a fast, affordable solution. Students lived and studied inside these repurposed military shelters, often sharing communal spaces and adapting the interiors for classrooms or dormitory-style living. By 1950, estimates suggest over 3,000 schools across the United States incorporated at least one Quonset classroom. Students spent entire school years learning under the curved steel ceilings, a direct extension of the wartime engineering legacy. Religious institutions found Quonsets equally practical. Exploding suburban populations demanded immediate worship spaces, but conventional church construction could take a decade. Congregations opted for Quonset huts, spending $2,500 for an instantly functional facility rather than $150,000 for long-term grandeur. First Presbyterian Church of Levittown, Pennsylvania, held services in a hut from 1952 until 1967, while other congregations made similar calculations. Acoustics were imperfect, aesthetics minimalist, but congregants gained a place to gather, pray, and organize community life without delay. Commercial and agricultural uses expanded rapidly. Small businesses, machine shops, and auto repair garages embraced the clear-span space offered by Quonset designs. Without interior columns, a single hut could accommodate welding equipment, storage racks, or automotive lifts. Farmers, particularly in the Midwest, adopted Quonsets for grain storage, livestock shelter, and equipment garages. The structures were low maintenance, requiring little more than an annual hose down and occasional bolt inspection, ensuring longevity even in harsh environments. The widespread civilian adoption of Quonset huts created an unexpected architectural legacy. What had begun as a wartime expedient became embedded in the visual culture of post-war America. Photographs, movies, and television often featured these steel tunnels as shorthand for practicality, ingenuity, and post-war optimism. Initially dismissed by architectural historians as temporary and unsophisticated, Quonset huts gained recognition in the 1990s as examples of adaptive reuse and vernacular architecture. Surviving units were designated as historic landmarks, honoring their dual legacy as both military innovation and civilian utility. In just a few short years, the Quonset hut had transitioned from a prototype engineered for survival in the Pacific theater to a versatile building form integral to American life. From the beaches of Guadalcanal to suburban neighborhoods and university campuses, these prefabricated steel arches provided affordable, durable, and rapidly deployable shelter. Their success demonstrated the power of combining industrial production, clever engineering, and practical field feedback, lessons that would continue to influence architecture, disaster response, and even modern prefab housing for decades to come. The legacy of Quonset huts did not end with post-war civilian adaptation. Their underlying principles, prefabrication, rapid deployment, and structural efficiency, remained relevant as disasters, conflicts, and humanitarian crises unfolded around the world. By the late 20th century, organizations responding to emergencies began rediscovering the same concepts that guided Quonset design in 1942. One of the clearest modern examples emerged in 2010 after the earthquake in Haiti. Hundreds of thousands were left homeless, infrastructure lay in ruins, and conventional construction was impossible. Relief organizations faced the same challenge that had confronted the U.S. military in the Pacific: provide immediate, durable shelter with minimal resources and unskilled labor. The solution borrowed directly from Quonset principles, even when designers were unaware of the historical connection. Prefabricated components shipped flat, arched steel frames providing structural integrity, and simple assembly techniques allowed teams to erect functional shelters in hours. Modern refugee housing units, such as RHUs, refugee housing units, are essentially 21st century Quonsets. Instead of corrugated steel, engineers use insulated composite panels that improve thermal performance in extreme climates. Connections employ snap-fit or bolt systems, minimizing the need for tools while maintaining structural integrity. Ventilation is carefully engineered to manage condensation and airflow in both hot and cold environments. Yet the core philosophy remains identical. Arched profiles resist wind forces, prefabricated units ship efficiently, and assembly is feasible for untrained personnel with minimal equipment. These shelters currently provide housing for over 200,000 displaced people across Africa, Asia, and the Middle East, proving the enduring utility of the Quonset concept. Hurricane response in the United States further validates the design's resilience. After Hurricane Katrina devastated the Gulf Coast in 2005, engineers analyzed which structures survived. Conventional rectangular homes were reduced to foundation slabs, while curved or arched metal buildings consistently withstood the winds with only minor damage. The findings reinforced what Quonset engineers had known decades earlier: aerodynamic architecture, which works with natural forces rather than relying solely on brute strength, drastically improves survival under extreme conditions. Curved surfaces reduce pressure coefficients, wind slides over the structure, and stress distributes evenly across the arch. The tiny house movement has also unknowingly embraced Quonset principles. Architects and manufacturers seeking maximum interior space with minimal materials frequently design arched, prefabricated cabins using corrugated metal or lightweight composites. These structures emphasize sustainability, affordability, and ease of assembly. Consumers rarely realize that the aesthetic and functional choices they admire in modern tiny homes trace their lineage directly to a World War II military shelter. Military applications have never ceased. The U.S. Armed Forces continue to deploy arch-style shelters in conflict zones from Afghanistan to Iraq, as well as in classified locations. Modern designs incorporate aluminum alloy frames, Kevlar-reinforced panels, and integrated climate control systems. Units can be helicopter-lifted to remote locations, rapidly assembled under fire, and survive blast waves or severe weather. Engineers in 2025 looking at these shelters would immediately recognize the design philosophy pioneered in Rhode Island in 1942. The arch remains the most efficient form for rapid deployment, durable shelter. Innovation continues even in extreme and experimental environments. NASA and private aerospace companies designing Martian habitats are independently rediscovering Quonset principles. Proposed Martian shelters feature prefabricated arches that ship flat on spacecraft, self-supporting structures that require minimal foundations, and components designed for assembly by small teams with limited tools. The extreme constraints of interplanetary construction, dust storms, low gravity, limited resources, mirror the logistical and environmental challenges faced on Pacific Islands in 1942. The same engineering solutions emerge, proving that the fundamentals of mass-produced, resilient architecture are timeless. Across all applications, post-war housing, disaster relief, modern prefab cabins, military shelters, and space habitats, the Quonset design philosophy remains strikingly consistent. Prefabricated arch structures combine efficiency, durability, rapid deployment, and affordability. Whether on Earth or Mars, in hurricanes or typhoons, these principles continue to guide engineers who must shelter people quickly and reliably. The legacy of 30 engineers working in a Rhode Island warehouse during World War II has proven both enduring and universal, demonstrating how a simple, elegant solution to a wartime problem continues to shape the way humans build and survive today. The Quonset hut's enduring success owes as much to its technical design as to the vision behind its rapid deployment. When engineers first began prototyping in 1942, they were solving a problem of survival in hostile environments, tropical heat, monsoon rains, typhoons, and the ever-present threat of enemy action. Each design decision was deliberate, driven by the dual need for structural resilience and logistical simplicity. The semicircular arch, borrowed from the British Nissen hut but radically simplified, became the defining feature. Unlike traditional rectangular buildings, where roofs push down on walls and rely heavily on foundations, the Quonset arch distributes both vertical and lateral forces evenly. Engineers call this the compression ring effect. The curved panels press against one another, transferring stress through the entire structure rather than isolating it in a few critical points. This innovation allowed a lightweight steel shell to withstand hurricane force winds exceeding 100 miles per hour and typhoons producing 20-foot storm surges. Corrugated steel panels were another critical innovation. The ridges running along the length of each panel function as mini I-beams, increasing rigidity and resistance to bending without adding excessive weight. When engineers tested prototypes, they discovered that 48-foot-long panels, weighing less than 50 pounds each, could be bolted together by small teams using only wrenches and simple hand tools. The corrugation also provided an aerodynamic advantage, helping wind to flow smoothly over the structure and reducing the risk of panels peeling away during storms. Material science played a crucial role. The original Quonset panels were painted steel, but exposure to salt air and humidity revealed early weaknesses, corrosion, rust, and panel degradation. By the Panama Canal Zone testing in late 1942, engineers had adopted hot-dip galvanization, coating steel in molten zinc at 850 degrees Fahrenheit. This metallurgical bond sacrificed the zinc before the steel beneath could corrode, extending operational lifespan from months to decades in tropical environments. The galvanized panels could flex slightly in storms without breaking, a critical property for buildings subjected to typhoons and earthquakes alike. Ventilation was another area of innovation. British Nissen huts had failed in the Pacific due to overheating in humid climates. Initial Quonset prototypes experienced similar issues, with condensation forming on cooler steel surfaces, drenching interiors overnight. Engineers responded with strategically placed ridge vents and end louvers, which created natural airflow without compromising structural integrity. Over time, field feedback led to enlarging these vents and adding interior fans or auxiliary openings when conditions demanded. These modifications ensured the huts were not just stormproof, but also habitable in extreme heat and humidity. Anchoring systems evolved with field conditions. Initial designs used simple steel stakes, effective in coral and sand but inadequate on volcanic soil or Arctic permafrost. Crews improvised, using oil drums filled with sand or tension cables connected to wooden sleepers, demonstrating the importance of adaptability. The engineering team back in Rhode Island codified these lessons, creating adjustable anchoring systems that allowed the huts to flex with ground movement, avoiding catastrophic structural failures during earthquakes or high winds. Insulation and cold weather adaptations became increasingly sophisticated. Arctic deployments in Alaska revealed steel brittleness at sub-zero temperatures and condensation problems from heating the interior. Engineers specified cold-rolled steel with alternative metallurgy for these environments, introduced rubber gaskets at every joint to maintain flexibility, and developed insulated batting for walls and roofs. Double-wall constructions, combined with controlled ventilation, preserved heat while preventing moisture accumulation. This adaptability allowed Quonset huts to operate from tropical islands to frozen northern archipelagos. The modularity of Quonset design was equally critical. Each 16-foot wide, 20-foot long section could be connected end-to-end or adapted for different uses, from barracks and hospitals to workshops and warehouses. Interiors could be outfitted with bunks, office equipment, or storage racks without altering the structural core. The design simplicity facilitated iterative improvements over time. Field modifications were routinely integrated into production, ensuring each generation of huts benefited from lessons learned in combat and civilian applications. Ultimately, the Quonset hut's technical evolution demonstrates the power of applying engineering rigor to practical problems. Each feature, from the arched panels and corrugated steel to ventilation, anchoring, and insulation, was the product of iterative prototyping, real-world testing, and continuous refinement. The result was a shelter capable of withstanding environments that would destroy conventional buildings, deployable by unskilled labor with minimal tools, and manufacturable in mass quantities. This combination of adaptability, resilience, and efficiency explains why the Quonset hut became a global architectural and engineering icon, influencing modern disaster response, prefab housing, and even extraterrestrial habitat design. The ultimate test of the Quonset hut came not in Rhode Island warehouses or laboratories, but on the battlefields and islands of World War II. Engineers could run calculations, simulate wind loads, or measure condensation, but nothing proved the design's worth like exposure to real combat and extreme weather conditions. From the humid jungles of the Pacific to the frozen Aleutian Islands and the war-torn towns of Europe, Quonset huts faced every environmental and tactical challenge imaginable, and adapted. Guadalcanal in August 1942 was the first major test for combat-deployed huts. Marine engineers unloaded flat-packed panels on a scorching beach under relentless heat and high humidity, surrounded by scorched coconut trees from previous bombardments. Within 12 hours, crews assembled 10 huts, providing shelter for aircraft maintenance teams operating F-4F Wildcats. 3 days later, Japanese bombers made a near miss. A 500-pound bomb detonated only 40 yards away. The blast wave shredded nearby canvas tents and splintered wooden buildings, yet the Quonset huts flexed and survived. Dirt and shrapnel rattled against the corrugated steel, but the interior remained intact, and the men inside emerged shaken but unharmed. This incident validated the compression ring concept, the arch distributed lateral forces, preventing catastrophic failure even under close-range explosions. Tropical conditions tested the materials further. Salt air and high humidity corroded ungalvanized fasteners within weeks, fungus began growing on moisture-retaining surfaces, and interior heat made the huts nearly uninhabitable without additional ventilation. Marines improvised, doors were left open, additional vents were cut, and field solutions were documented and sent back to Quonset Point. Engineers incorporated these adjustments into later production runs, larger louvers, fully galvanized fasteners, and improved ventilation patterns. Showing a remarkable feedback loop from field performance to industrial manufacturing. Iwo in February 1945 presented an even more extreme scenario. Volcanic black sand made conventional stake anchoring impossible, and artillery from Mount Suribachi posed a constant threat. Construction battalions adapted by filling oil drums with sand and connecting them to hut bases with cables. When a Pacific typhoon hit with 110 miles per hour winds, these improvised anchors held firm while wooden structures disintegrated, proving that flexibility in deployment methods could be as critical as structural design. The Quonset hut's modularity and simplicity allowed engineers and field crews to respond to unique environmental challenges without redesigning the core structure. The Arctic environment forced a different set of innovations. The Aleutian Islands campaign exposed Quonset huts to sub-zero temperatures and high winds. Steel became brittle, and early panels cracked at bolt holes. Engineers quickly switched to cold-rolled steel with improved metallurgy and introduced rubber gaskets to maintain flexibility at extreme cold. Insulated bats were added to the interior, while double-wall construction and controlled ventilation prevented heat loss and condensation. These changes made Quonset huts not just functional, but survivable in polar extremes, a testament to the adaptability of the original design. Europe introduced combat-induced stress testing. In Sicily, a Quonset hut serving as an ammunition depot took a direct hit from an 88mm German artillery shell. The projectile penetrated the steel skin and detonated inside among crates of munitions. The blast twisted the arched frame but left it standing, unlike rectangular buildings, which would have collapsed completely, crushing anyone inside. The arch compression ring and evenly distributed stress absorbed the explosion's energy, proving that even in catastrophic scenarios, Quonset huts offered a unique combination of durability and occupant protection. Iterative improvements continued throughout the war. Field reports highlighted minor flaws and vulnerabilities that could be corrected in subsequent manufacturing runs. Ventilation louvers grew larger, fasteners were fully galvanized, and interior insulation options were added for cold zones. Anchoring systems became more adaptable to varying soil and sand conditions. Every adjustment was tested, documented, and integrated, creating a continuous cycle of refinement that ensured each generation of Quonset huts performed better than the last. By 1944, Quonset huts were standard across multiple theaters of war, housing millions of personnel, protecting equipment, and providing operational infrastructure faster and cheaper than any alternative. Their performance under extreme conditions, typhoons, hurricanes, tropical heat, Arctic cold, enemy fire, and explosive blasts, validated decades of engineering theory and wartime experimentation. More than just a shelter, they became a logistical and strategic asset, enabling rapid expansion of bases, airfields, hospitals, and supply depots across the globe. The Quonset hut's legacy in field performance demonstrates that architecture is not just about form, but about solving real-world problems. Its adaptability, resilience, and efficiency emerged from the interplay of rigorous engineering, real-time prototyping, and relentless field feedback. This iterative process transformed a simple semicircular steel structure into one of the most successful and versatile shelters in history. With the end of World War II in 1945, the Quonset hut faced a new challenge: survival in peacetime. The United States military suddenly possessed roughly 170,000 of these versatile structures scattered across 6 continents, originally intended as temporary wartime shelters. The plan had been simple: decommission, scrap, or abandon them once permanent facilities could be built, but reality proved far more complex. For military commanders and local communities, the huts were no longer temporary expedients, they were immediately functional, cost-effective buildings ready to meet the pressing demands of post-war life. The housing shortage in the United States was severe. Returning veterans faced cramped living conditions, families doubled up in small apartments, and construction industries were starved for both labor and materials. In this context, Quonset huts became an unexpected solution. The War Assets Administration, responsible for liquidating surplus military property, found that demand for these prefabricated steel shelters exceeded supply. Veterans and civilian buyers quickly recognized that a Quonset hut, available for $1,000 to $2,500, offered a complete, weatherproof home that would otherwise cost $8,000 or more if built conventionally. Suburban developments sprang up around Quonset huts. In Los Angeles, Roger Young Village housed 750 families in converted military structures. College towns, swelling with students taking advantage of the GI Bill, repurposed Quonset huts for temporary dormitories and classrooms. Families modified interiors, adding partitions to create bedrooms, living rooms, and kitchens. Curved steel walls were adapted with windows, doors, and wooden facades to improve aesthetics while maintaining structural integrity. Some homeowners even buried huts partially into the ground for insulation or connected multiple units to create larger compounds. Municipalities, initially hesitant, relaxed building codes in response to urgent housing needs, allowing these innovative adaptations to flourish. Quonset huts also found applications beyond housing. Churches embraced them as temporary sanctuaries, providing space for congregations without decades-long fundraising campaigns. First Presbyterian Church of Levittown, Pennsylvania, held services in a Quonset hut from 1952 to 1967, a pattern repeated by dozens of congregations nationwide. Schools, particularly in rural districts, converted huts into classrooms to meet the educational demands of the baby boom. A single Quonset hut accommodated 30 students at roughly one-tenth the cost of traditional construction, allowing rapid expansion without compromising functionality. Commercial and industrial sectors quickly recognized the benefits of Quonset huts. Small businesses, repair shops, warehouses, and agricultural operations leveraged the open-span interiors and minimal internal supports for practical purposes. Farmers used them to store equipment, livestock, and grain. Machine shops and auto repair garages set up operations in surplus huts, avoiding months of conventional construction and reducing overhead costs. Their durability, low maintenance, and flexibility made them a natural fit for both urban and rural applications. Culturally, Quonset huts became embedded in American life as symbols of ingenuity and practicality. Initially dismissed by architectural historians as temporary eyesores, they gradually gained recognition for their adaptability and historical significance. By the 1990s, preservationists began designating surviving huts as historic landmarks, celebrating their role in both wartime logistics and post-war civilian life. Movies, television, and photography immortalized their distinctive curved profiles, cementing their place in visual culture as reminders of a period when necessity drove innovation. The Quonset hut's influence extended beyond the United States. Governments, humanitarian organizations, and military forces worldwide adopted the concept of prefabricated, arched steel shelters for disaster relief, refugee housing, and rapid military deployment. The 2010 Haiti earthquake highlighted the enduring relevance of these design principles. Architects and aid organizations built shelters using arched frames, flat-pack components, and minimal tools, echoing the logistical problem-solving of 1942. Modern RHUs, refugee housing units, borrow directly from Quonset concepts, incorporating insulated composite panels, snap-fit assembly, and rapid deployment capabilities. Even in developed nations, hurricane and typhoon-prone regions turned back to arched steel shelters. After Hurricane Katrina devastated the Gulf Coast in 2005, researchers noted that curved, self-supporting buildings outperformed conventional rectangular homes, mirroring the wind-resistant principles pioneered in Quonset huts decades earlier. Architects and engineers now refer to this approach as aerodynamic or resilient architecture, demonstrating that the physics behind the Quonset hut remain relevant in contemporary design and disaster response. Ultimately, the post-war adoption of Quonset huts represents more than a historical curiosity. It is a case study in adaptability, rapid deployment, and the enduring value of engineering solutions that prioritize practicality, cost efficiency, and resilience. From suburban housing developments to global disaster zones, the legacy of Quonset huts extends far beyond their wartime origins, proving that a simple curved steel shelter can meet complex human needs across decades and continents. The Quonset hut's design principles continue to shape architecture, disaster response, and even space exploration nearly a century after their inception. What started as a wartime necessity has become a blueprint for efficient, resilient, and adaptable construction. The physics that drove the original 1942 designs, curved steel arches, self-supporting structures, flat-pack shipping, and rapid assembly, remain as relevant today as they were in the jungles of Guadalcanal or the Aleutian Islands. Modern prefabricated housing borrows heavily from Quonset architecture. Tiny homes, disaster shelters, and modular cabins often feature the same semicircular roof profile, maximizing interior volume while minimizing materials. Companies market these structures as sustainable and cost-efficient alternatives to conventional construction. They utilize advanced materials, lightweight aluminum alloys, composite panels, and high-performance insulation, but the core geometry remains unchanged. The curved profile distributes loads efficiently, resists extreme winds, and allows for rapid construction, echoing the very challenges faced by engineers during World War II. Disaster response agencies around the world continue to apply Quonset-inspired designs. The UN's refugee housing units, built for camps across Africa, Asia, and the Middle East, are essentially modern Quonset huts. These shelters are prefabricated, lightweight, and designed for assembly by unskilled labor with minimal tools. Ventilation systems, insulated panels, and snap-fit connections replace 1940s fasteners and steel sheets, but the logic is identical: create durable, deployable shelter for maximum occupancy with minimum cost and time. A two-person crew can erect these units in 4 hours, mirroring the efficiency benchmark set by the Navy's construction battalions in 1942. Hurricane-prone regions have rediscovered the advantages of curved structures. Following Hurricane Katrina in 2005, engineers observed that traditional rectangular homes collapsed under wind and water forces, while Quonset-style shelters survived with minimal damage. This empirical evidence led to renewed interest in aerodynamic architecture, designing buildings to work with environmental forces rather than resisting them through brute strength alone. Researchers noted that curved roofs deflect wind, reducing pressure differentials that cause catastrophic structural failure. The legacy of the Quonset hut lives on in these observations, validating the wartime lessons of resilience and adaptability. In the commercial sector, Quonset-inspired designs enable rapid deployment of workshops, warehouses, and agricultural buildings. Modern variations feature adjustable panels, insulated walls, and modular configurations, allowing businesses to expand or relocate quickly. Farmers, for instance, install arch-shaped storage for grain, livestock, or machinery, appreciating the clear-span interiors without internal supports. Industrial users exploit the same benefits: large open spaces, rapid construction, and low maintenance costs. The Quonset hut's combination of simplicity, strength, and adaptability ensures its relevance across decades of civilian use. Even space exploration demonstrates the enduring influence of Quonset principles. NASA and private space companies, tasked with designing habitats for the Moon or Mars, face constraints remarkably similar to those in the Pacific Theater of 1942: extreme environments, limited materials, prefabricated components, unskilled assembly, and minimal tools. Proposed Martian shelters feature arched frames that resist dust storms, prefabricated panels for flat-pack shipping, and self-supporting structures that don't require deep foundations. Engineers repeatedly arrive at solutions that mirror the Quonset hut, proving that the constraints of physics, materials, and logistics naturally lead to the same design logic, even on another planet. Luxury architecture has also adapted the Quonset profile for aesthetic purposes. Floor-to-ceiling glass end walls, premium finishes, and climate-controlled interiors transform the original wartime shell into modern homes, offices, or event spaces. Despite the high-end appearance, the fundamental structural principles remain unchanged: an arched, self-supporting frame, efficient load distribution, and rapid construction potential. This evolution from military necessity to civilian sophistication underscores the versatility and timelessness of the original engineering insights. The Quonset hut story is ultimately a testament to problem-solving under pressure. In 1942, engineers faced an impossible logistical and environmental challenge: provide shelter for millions of soldiers across hundreds of islands with limited materials, manpower, and time. The solution was not incremental, it was revolutionary. By combining lightweight materials, prefabrication, modularity, and arch-based engineering, they created a building that was faster, cheaper, and more resilient than anything conventional construction could provide. From the battlefields of World War II to modern disaster relief, suburban neighborhoods, industrial applications, and extraterrestrial habitats, the principles pioneered in a Rhode Island warehouse remain surprisingly relevant. The Quonset hut is more than a historical artifact. It is a blueprint for efficiency, resilience, and adaptability, proving that innovative engineering can transcend its original context to solve problems across time, geography, and even planets. In the end, the legacy of Quonset huts is not only in the steel that still stands on Earth but in the enduring philosophy they embody. Simple, clever, and resilient solutions to complex, urgent problems can reshape industries, communities, and even the future of human habitation.